This video is an introduction to chemical kinetics and rates of the reaction. Okay, so reactions can occur very slowly or very, very quickly. The reactions that are here should happen. They are thermodynamically favorable, which means that they should happen, but we don't see them happen. And so there's a few reasons, or we don't see them happen quickly. There's a few reasons why. Most of the time it's simply because the kinetics, the rate of the reaction is so slow that we don't see it happen very quickly. So just like changing diamond to graphite, that's right, so a diamond ring wants to be pencil lead. These reactions appear spontaneous, they just don't happen very quickly, so we won't see them happen if we watch them. So how fast a reaction happens or how slow is called the rate of the reaction. This area of chemistry is called kinetics, and it's extremely important in medicine and biochemistry. So in really any form of chemistry, we're looking for reactions that happen at a reasonable rate. Otherwise, there's no reason to perform that reaction at all. So there's lots of other areas of chemistry that use kinetics experimentally to determine if a reaction is worth the time it takes to perform it. And if the reaction happens slowly but it's favorable, then we would add something to it to make it happen faster. All right, so one of the main goals for studying kinetics is to help understand how the reaction takes place, how many steps of the reaction occurs when it's going from reactants to products, and that's called the reaction mechanism. So we'll study reaction mechanisms at the end of this. And if you go further into chemistry and you take organic chemistry, most of organic chemistry is looking at the different mechanisms that are occurring and then how to determine experimentally what products you're forming by looking at the different spectra that's given by the instruments used in labs. But anyways, in this course, we're going to look at different mechanisms and what mechanisms are, and we're going to look at the rates and how we can determine how much product is going to be made and stuff like that. Okay, so right here, we're given a table, and we started off with nitrogen dioxide. That's not nitrite, that's nitrogen dioxide. There's no charge on it. And so this reaction is producing nitrogen monoxide and oxygen gas, and it's happening at 300 degrees Celsius. Well, that's not important for the calculations. It's given to you to show you that the temperature is not changing. All right, so we're starting off with this, and it's decreasing over time, so it's going away as a reactant should to form its products. And then our two products here are increasing, right? So if we graph that and we put time on the x-axis and we put the concentration of our substances on the y-axis, these two right here, so this teal colored one is the nitrogen monoxide is increasing, as well as the oxygen here is increasing, and then the nitrogen dioxide is decreasing, right? So if we were to find the slope of the tangent line, we could find an instantaneous rate at any point during this reaction for that substance. That's really not as hard as it sounds, so don't give up on me yet. It's fairly easy. All right, and one thing that I want you to notice when you look at this is nitrogen dioxide or nitrogen monoxide here is increasing twice as fast as oxygen is, and that really is because of its mole to mole ratio. 2 moles of this have to get produced for every 1 mole of this that's produced. So we would expect to see this increase faster than we would this. All right, so reaction rate, the change in concentration of reactant or product per unit time. So if we have a concentration of A at a particular time, we'll call it time 2, when we subtract from that the concentration of A at time 1, and then we divide it by the difference in times, we would get rate. And so it's the change, delta, in the concentration of A. So concentration in kinetics is represented by these brackets. Okay, it's in chemistry all the time. Brackets mean concentration or molarity, and divided by the change in time. So it's slope, right? Because we would have A would be, the concentration of A would be on your y-axis, and the time would be on the x-axis. So it's change in y over change in x. All right, and this would give you an average rate change, average rate of reaction. So typically reaction rates are given as a positive number, although I have seen some textbooks represent them negative if it's a reactant. And technically a reactant should have a negative rate and a product should have a positive rate, but because the way things are worded, we don't always show that. All right, so this problem right here, question 1, says, using the data on the previous slide for the reaction above, how does the concentration of nitrogen dioxide change in the first 50 seconds? So in the first 50 seconds, that means we start at time 0. So time 1 would be 0, and time 2 would be 50 seconds. So that means I need to find my concentrations for those times. So if I go back and look at the table, feel free to pause the video and go back and look for yourself if you want. But in that table, for NO2, at 0 seconds, we started out with 0.01 molar. And at time 50 seconds, we have 0.0079 molar because it's decreasing, right? It's one of the reactants. Here's the reaction in case you don't remember it. Over here down to your left. So since it's a reactant, the concentration should go down, and it does. It went from 0.01 to 0.0079. So I'm going to use this equation up here, right? And I am going to plug in 0.0079 minus 0.01. Those are my molarities, so it's the change in molarity over the change in time, 50 minus 0. So it doesn't matter what order you subtract them in. Remember slope. It just, as long as it's the same on the top as it is on the bottom. And so these 2 points, that is 1 point in the graph, right? That's the y value and that's the x value. And then this is the y value and this is the x value. So you have to do it in the same order. So I did second minus first, and then the second time minus the first time. So this is the second molarity minus the first molarity, second time minus the first time. And so if I end up subtracting those and then dividing it out, I get negative 4.2 times 10 to the negative fifth, and that would be molarity per second, because I have molarity up here and seconds down here. And so that is the rate of change for the concentration of NO2 in that reaction. And I just want to reiterate the reason why we used NO2 is because it specifically asks for NO2, and the reason why we used those particular concentrations was because in the table those are the ones that are related back to these times. Right, so and it said the first 50 seconds, so that's from 0 to 50 seconds. If it was the second 50 seconds, we would go from 50 to 100. Or if it said from time 25 seconds to 100 seconds, we would use those values for time, and we would use those corresponding concentration values. How is the rate of each substance in the reaction related to one another? So if we look at this reaction, like I said before, the rate that this disappears, so the rate of consumption of NO2 would be the exact same as the rate of appearance or the rate of production of nitrogen monoxide, because this is 2 and this is 2. And then oxygen would be half of the rate of these other two because it's only 1 oxygen is produced for every 2 of these that are consumed or produced. And so let's look at that a little closer with a different reaction. All right, I've got 1N2 plus 3H2 to give me 2NH3, and we want to know how the rates of the substances in that reaction are related to one another. So this is where kinetics starts to get weird, and they start to make it look like something different, but it's not. It's the same stuff you've been doing since the beginning of chemistry with mole-to-mole ratios. But let me show you how they show it to you sometimes. So if I look at the rate of consumption of N2, that would be a negative rate, and it would be the change in the concentration of N2 over the change in time. And then the rate of H2 would be 1/3 of that. So it'd be equal to negative 1/3 times the change in the concentration of H2 over the change in time. And that would be equal to positive 1/2, because NH3 is being produced, change in the concentration of NH3 over change in time. So they're taking these coefficients and they're inverting them to make an equation instead of doing a mole to mole ratio. But let's just say that I wanted to find the rate of change for NH3. So I wanted to find delta NH3 over delta T, okay? I wanted to find this. So I'm going to look at this equation here, and so it'd be negative 1/3, and I'm just going to, in terms of H2, in terms of H2. So this equation up here that I've written, you could write it like this, just for those two. Right? And if I'm looking for this, so if this whole thing is my x value, then in order to solve for that, I would multiply by 2 on both sides. So the 2's would cancel out over here, and I'd have my x alone, and then I would have negative 2/3 change in H2 over change in time is equal to my change in the concentration of NH3 over time, change in time. So this looks funny, but guys, it's just a mole to mole ratio. So let's say that I have this value, right? And I want this. So if I have this, that's what I would write down, because that would be my given. And then I would say 2 mole or 3 moles of H2 over or under 2 moles of NH3. That's a mole to mole ratio, and it's the exact same thing that I have written here, and that would give me the moles of NH3, right? Because this concentration here, let me erase that so you can see. It would be molarity, right? Moles would be up here, and then liters would be down here, and this would be moles of H2. So it's the change in moles of H2 over liters times change in time. So this moles of H2 goes away, and I end up with this. So you might see it written this way, so you might want to know what it means, but you don't have to use that. You can just use your mole to mole ratios, and that's how I'm going to use it when we have to find these in the problems in here. All right. Okay, so in this first one, we've got this reaction, and it says we have 0.0048 moles of pH3 in a 2-liter container, and it's consumed every second of the reaction. And we want to know the rates of P4 and H2. So before I can find these, I have to figure out what the rate is for this. And so I need to find molarity first, because rate of a reaction has the units of molarity per second. So I need to know how the molarity is changing every second. So first, this is moles, this is liters. I need to put it in terms of molarity. So the molarity of pH3 is going to be 0.0048 moles of pH3 divided by every 2.0 liters. And so that's going to be 0.0024 molarity pH3. And that is changing every second. So that's my rate per second. I can divide by 1 second. So that's my rate of pH3. Now if I wanted to go back and calculate the rate of production of P4, then I can say I've got 0.0024 molarity per second of pH3, and then look at my mole to mole ratio, 4 of these for 1 of these. I would get 6.0 times 10 to the negative 4th molar P4 per second. The seconds is still there. The only thing that canceled out is the moles of pH3, and it was replaced with moles of P4, so liters and seconds are still there. And then we're going to do the same thing for H2. So 0.0024 molarity of pH3 per second, and we've got 4 moles of pH3 for every 6 moles of H2. So 0.0024 divided by 4 times 6 is 3.6 times 10 to the negative third. And so both of those are positive. They're both being produced. So this one's 6.0 times 10 to the negative 4 and 3.6 times 10 to the negative 3. All right, next problem. It says calculate the average rate of decomposition of hydrogen peroxide between 0 and 2.16 times 10 to the 4 seconds, and use that ratio to calculate the average production of oxygen. So first, I see that this is going from 1 to 0.5, and this one is going from 0 to 2.16. So I have to do my change in concentration over change in time. So it's 0.500 minus 1.00 divided by 2.16 times 10 to the positive fourth minus 0. And that's molarity up here. And down here is second. So that is going to give me 0.5 molar over 2.16. That's negative. Times 10 to the 4th seconds. And then if I do the math there, I get 2.31 times 10 to the negative 5th molarity per second, and that's for the H2O2. Now if I want to find out for this oxygen here, then I'm just going to use a mole-to-mole ratio. So I've got 2 moles of H2O2 for every 1 mole of O2, and I got that from the equation right here, up here. So it's going to be half. So the answer is 1.16 times 10 to the negative 5th molarity per second. All right, and then the last problem is kind of a little tricky problem. I don't know that something like this would ever be on there, but it could be. I found a problem like this in a textbook, and I thought it was pretty clever, so I added it. All right, so we have these rates. So this is the reaction. We have A plus B goes to C, and this one is a reactant, so we put a negative here, and this is a reactant, so we put a negative here, and this is a product. But we don't know what the coefficients are, little c, little v, and little a, and we want to find them. So in order to do that, we have to basically look at the ratios of production here. And I'm going to take the smallest number and compare it to the other numbers. So the smallest one is the 0.008. It's smaller than the other two. So I'm going to divide 0.008 into all of these and compare them. So this one is 1. Right, 0.008 goes into 0.008 one time, and this one is 1.5, 0.012 divided by 0.008, and this one is 2. And so those are our coefficients, except you can't have a 1.5 for a coefficient, so all of these are going to double. So the coefficient for capital A would be 2, because this has to be doubled, and this would have to be doubled, and this would have to be doubled. So 2 A's plus 3 B's gives me 4 C's. So that's the reaction. And that's it for this. It's pretty simple. It's pretty straightforward. The only thing confusing about this is the way that they write those, how the rates are related to one another. But if you can just remember to put the coefficients on the bottom as inverse, then you should be fine.